Hello everyone, welcome back to another lecture of Chemical Process Design and Simulations course code CHE 446. And as you know, there are four series of this course: Fundamentals, Simulation, Analysis, and Design. And this lecture will cover various topics: composite curves, how we draw the composite curve. In our previous exercise, we have taken two stream example. We have used graphical method and we have used problem table approach to find the utility requirements, pinch temperatures for hot and cold stream. But now we have more than one hot and one cold streams, or overall we have 4, 5, 6, 7, and so on process streams. Then how to draw graphical method or composite curve for these we will see today. And in the same lines we will use the problem table approach. Then we will draw grand composite curve. This is the new part for today, the data extraction from a flow sheet, how we can extract the data from a flow sheet, and then the further exercise part. So to handle multiple streams, what we need to do, we need to add their heat loads or heat capacity flow rates of all streams existing over any given range of temperature. And then a single composite curve of all hot streams and a single composite curve of all cold streams can be produced in a TH diagram like this. That for example, you have two hot streams and two cold streams. Just like the fundamental where you have one line for cold and one line for hot, you have to convert the number of streams to one line. Like for example, as you can see, this line is presented like this, then it turned this, and then it turned this. It shows it is not a one stream, it contains more than one stream, and these are aligned in this way. Similarly, the cold streams are aligned in this way, and how these are aligned we will learn it today. And this region, this one, this end to this, and this end to this shows the heat recovery region or the process to process heat recovery potential of this system. And this, the upper part, which is on the cold side, shows the hot utility requirements, which is the minimum requirement, which is unavoidable requirement of the system. And this one, which is on the hot stream, shows the cold utility requirement, which is the minimum cooling utility requirement for this on the temperature enthalpy diagram. So this is the overall representation of it, and the difference between these points shows the value of delta T minimum. If we decrease this value, then these two curves will come closer. If we increase these values, these curve will separate, and once these come closer, this requirement will decrease, as you can see, and once these expand, these requirements of utilities will increase. Now, how we can combine all this? As you can see, there are three streams: A, B, and C. This stream, which is A, is from T2 to T5. B is from T1 to T3. C is from T2 to T4. We have to calculate delta H of each interval. How? If you remember the problem table approach, how delta H is calculated by multiplying Cp multiplying by the temperature interval. Here we will not be subtracting. Here we will be adding. How? That this is the first region, which is from T1 to T2, and which stream is it containing? B. So it will be T1 minus T2, the temperature interval, multiplying this Cp of B. Then this interval T2 and T3, it is T2 minus T3, and B, C, A, three streams are involved, so all their Cp's will be added up. Then T3, T4, C and A streams are added, A plus C, T3 minus T4, and in the last region or last interval, which is T4 to T5, T4 minus T5 multiplied by A. And then this one becomes delta H1, delta H2, delta H3, and delta H4. Four regions: 1, 2, 3, 4. Four intervals. So four calculations of delta H. And this line is drawn over here. Now we will look at the actual stream data and we will plot TH diagram for these composite curves. Stream number 1, that the cold stream, is from 20 to 135 degrees centigrade with a Cp value of 2. The hot stream 170 to 60. 3 Cp value, cold stream 80 to 140, Cp value is 4, and hot stream 150 to 30, Cp value 1.5, and the delta T minimum for this system is 10 degrees centigrade. Now, there are two hot streams, there are two cold streams. Earlier, it was very straightforward. We have to draw the two lines and adjust these. But now, for this system, we have two hot streams and two cold streams. So, how we can draw it? First, we need to see it, and we will calculate the heat load. In the previous slide there was no heat load calculation. But now there is a heat load calculation, 230 kilowatt heat load over here, 330, 240 and 180. So you can see that for a hot streams, the total heat load is 510 kilowatt, 330 plus 180. Obviously, ignore the minus sign over here. That shows the direction. And 230 plus 240, it is 470 kilowatt. So 470 kilowatt for cold stream, 510 kilowatt for hot stream. When we draw a single line for these two streams, hot, then the total heat load should be 510 kilowatt. And in the same way, when we have drawn it for cold stream, it should be 470 kilowatt. So first we will draw the graph paper. Obviously you need a graph paper to solve this. Heat load is on x-axis, temperature on y-axis. We will first draw the lines 170 degree centigrade, 150 degree centigrade, 60 degree centigrade and 30 degree centigrade. And from where these came, as you can see 170, 60, 30 and 150. So first we need to draw this diagram for our simplicity and to divide it into intervals. So as you can see there are three intervals. One which is from 170 to 150, 2 which is from 150 to 60, 3 which is from 60 to 30. Now the first stream is from 170 degree centigrade to 60 degree centigrade with a heat load of 330 kilowatt. I had told you, if you remember in our previous lecture, that the total heat load should not be violated. This line cannot be from here. Obviously, it will be at 170, but the heat load here is 270. Well, the actual heat load is 330. So 330 kilowatt, initial temperature 170 degree centigrade, final temperature 60 degree centigrade. And then the second one, which is of 180 kilowatt, from 150 degree centigrade to 30 degree centigrade. Now these two lines are crossing each other. There is no issue because these two are hot streams. And we have to make it into one single line. So this is the first interval. And which stream is involved? The first one, whose CP value is 3. In this region, both these streams are involved from 150 to 60. So 3 plus 1.5, 4.5. And in this region, only green stream is involved, which is the second stream of CP 1.5. So what you need to do? You need to multiply 3 by 20. So it means here delta H is 60. 170 minus 150. 20 multiplied by 3, 60. Then 150 minus 60, 90. 90 multiplied by 4.5, 405. So 405 here, 60 here. It means it will be 465. 60 minus 30, 30 multiplied by 1.5, 45. So 465 plus 45, 510. So as you can see, the total heat load calculated by here is accomplished. How? Let's go to the next slide. And the same way, these are drawn. Delta H is 60, 405 and 45, which I have shown you in the previous slide. Now, point to be noted that we have to make it as one line. So it means that the line should start from 510 kilowatt and it will end at 0 kilowatt. So it will be from 0 to somewhere around here 510 kilowatt, because the total heat load of this system, of the hot stream system, is 510 kilowatt. So it means the initial temperature will be 170 degree centigrade to here. Now, how we have decided this point? Because if you see 510 minus 60, 510 minus 60 will be 450. If you can see it, that the initial heat load or the overall heat load was 510 kilowatt. First, we need to subtract 60 from 510. So what it will end it at? 450. So we have drawn a line from 170 and ended up at here. And it should end here because it is our interval. It should stay within the interval. It is not like that you end here or you end here, because you will violate the interval. You have to remain within the interval of 170 to 150 degree centigrade with initial heat load as 510 and final heat load as 450. When you subtract this, it is 60. Now from 450, you minus 450 from 405, what it will be? 45, which will come around here and it will should stay within the interval. So as you can see, it is 45. And the last one, simply connected. So as you can see, a single line is drawn for two hot stream system. And this is the very simple method. When you have more than two hot streams, the same procedure will be adopted. You have to draw the intervals. You have to calculate the CPs or added the CPs, then multiply with temperature interval. and drawing line. Now similarly for cold stream, these intervals have been used. Again, there are three intervals, this one and this one. CP is 4, CP is 6, CP is 2. How the same procedure is adopted over here. Maroon line, its CP is 4. Orange line, its CP is 2. So as you can see in this region only there is orange line, so its CP is 2. Here both lines are involved, so CP is 6. Here only maroon line is involved in this region, so CP is 4. Now, for this system, the total heat load was, if you remember, was 470 kilowatt. So as you can see, it is at 230 kilowatt and it is at 240 kilowatt. So a total of 470 kilowatt. Now, this stream 20 to 135 and 80 to 140, 240 and 230 kilowatt. Now, in the same fashion, this is 140, 135, 80 and 20. Delta H is 20 over here, 330 and 120. So it shows that total sum is 470 kilowatt, and you have to start from somewhere around here, and your initial temperature should be from this to this, 470 to 450. If you subtract this, it will be 20. Then 450 minus 330, it will be 120. So it is somewhere around here. Obviously, if you have a proper graph paper, then you can have accurate calculations, and the remaining 120 will be from this point to this point. So this is how the cold line has been drawn. I hope that the overall procedure is clear to you, that how these lines have been drawn in the system. Now we have drawn all the lines over here because we have to show it on one single graph. We have first drawn the hot streams, then we have drawn the cold streams, and now we have to draw both these streams on a single line. So this is how the hot was drawn, and this is how the cold was drawn. Now, initially, it will look like this. And as I told you, at every point, the hot temperature should be higher or can be equal. Obviously, at that point, the value will be of heat exchanger requirement will be high, but it should be at every point should be higher. And as you can see in this region, it is crossing. So what you need to do, you need to just take it away a bit. And if I, for example, take it on, you have to take all of it, not just single line. Like आपने सिर्फ ये जो इस region वाली line है इसको नहीं लेना. You have to take all this green line to it. And as you can see at this point, there is a delta T minimum of 0, as both these lines are just intersecting or touching each other. So this point is known as the point at which the delta minimum is 0, and it corresponds to 80 degrees centigrade. Now, for a value of delta T minimum of 10 degrees centigrade, you have to vary it. Have you been able to achieve it over here? This value corresponds to 80 degrees centigrade for hot stream. The blue line, the red line is somewhere around 85 or 86 degrees centigrade, which corresponds to a temperature difference of 6. No, it is not achieved yet. So you have to take it more on the right side. And now if you see at this point, somewhere at this point, you can see that at this point, as you can see, the temperature is 90 degrees centigrade for hot stream. For cold stream, it is 80 degrees centigrade. So this corresponds to a temperature difference of 10 degrees centigrade, which is our requirement. So as you can see, at this point, we have achieved our required delta T. And obviously, why we are taking this point? Because this point was interacting with this line, and now we have to see at this point, which is the minimum temperature difference. Obviously, you have got higher temperature difference in this region, higher temperature difference in this region, but the minimum temperature difference at a single point is less than 10 degrees centigrade when the line was here. But now once this line has come forward, you can see at this point it is 10 degrees centigrade. And now if I label it like this, then you can see that this region, this whole region represents the heat recovery, and this region represents the cooling utility requirement, and this represents the heating duty requirement. So as you can see, this corresponds to 510, this corresponds to 530. So 20 kilowatt heating utility requirement, and this corresponds to nearly 60 kilowatts. So this corresponds to cooling utility requirement, and the hot pitch temperature is 90 degrees centigrade. The cold pitch temperature is 80 degrees centigrade. The heating utility requirement is 20 kilowatt. The cooling utility requirement is 60 kilowatt. So this is how you draw a composite curve on TH plot for a 4-stream system in which there are 2 hot and 2 cold. Now we will apply this on problem table approach, and we will see whether we get the same answers or not. Now for the problem table approach, we know that we need shifted temperatures. And since the delta T minimum is 10, as you remember that for hot side or for hot stream, we subtract by delta T minimum over 2, and in cold stream, we add delta T minimum over 2. So we have to add a factor of 5 in cold streams and subtract from hot streams. So 20, 25, 135 becomes 140. This 176, 165, 60 becomes 55. 80 becomes 85, 145, 145 and 25. Now you can see there are some identical values, like 25 is coming two times, 145 is coming two times, so that won't make any difference. Now we know the values. One is 165, then 145, 140, 85, 55 and 25. So first we need to draw the intervals over there. These are the values: 165, 145, 140, 85, 55 and 25. And then you have these intervals, as you can see, 1, 2, 3, 4, 5 intervals over there. The first stream, which is a cold stream, is from 25 degrees centigrade to 140 degrees centigrade, shifted wise. Then second stream, 165 to 55. Then third stream, 85 to 145. And then fourth stream, 145 to 25. Then in the same way, we have to draw the intervals, and I have placed their CP values, and I had explained it in the previous lecture that this negative is just for the simplicity, because we are following the nomenclature summation of CP of C minus summation of CP of H. Its CP is 2, 3, 4 and 1.5. And the interval 165 minus 145, 20. This one 5, 140 minus 85, 55, 85 minus 55, 30, and 55 minus 25, 30. After getting that interval, we have to specify this value summation of CP of C minus CP of H. Now, in this first interval, there is only a hot stream whose CP is 3. So, and there is no cold stream. So, 0 minus 3, it will be minus 3. Similarly, in this region, the second one, there are 3 streams, 2, 3, and 4. So, 4 minus 3, 1, 1 minus 1.5, minus 0.5. Then in the third region, there are 4 streams, and similarly 1.5, minus 2.5 and zero point 0.5. And multiplying these two, 20 multiplied by minus 3, it will be minus 60, minus 2.5, 82.5, minus 75 and plus 15. We have already discussed in detail, and there is not a significant difference. As you can see, only number of streams or number of points have increased, but the overall procedure is same. And which one is surplus or deficit? Obviously this one, it is surplus of negative, negative surplus, positive deficit. So surplus deficit have been calculated. Now again, this is the same temperature interval. Hot utility is at top, cold utility at bottom. This minus 60, minus 2.5, 82.5, minus 75, 50. We have already calculated in the previous slide. And if you remember, we had said that we will take this first point as 0 and we will simply subtract it. So 0 minus 60, 0 minus minus plus 60, because it has already minus sign with it. So plus 60, 60 minus minus plus 60 plus 2.5, 62.5, 62.5 minus 82.5 minus 20, then 55 and then 40. So which one is the lowest value among these? 20. So we will target this point and we will take it as here in the feasible cascade. This is the infeasible cascade because there is a one value with the negative sign. And then this interval, the same value as that of here. And now we will take 20 over here. So it is plus 20. Now 20 minus minus 60. So it will be 80. 80 minus minus plus 82.5. 82.5 minus 82.5, it will be 0. 0 minus minus plus 75 and 75 minus 15, 60. So the upper value, first it's a visible cascade because all the values are positive over here. Then the upper value represents the hot utility, which is 20 kilowatt. The lower value or the end value represents the cold utility, which is 60 kilowatt, and you have calculated these values in the graphical method as well. Pinch temperature corresponds to that point at which in feasible cascade you are getting a 0 value, which corresponds to a temperature of 85 degrees centigrade. And if you remember, we had to now return the values, and how we return it? By adding 5, which is the delta T minimum over 2, because in this case delta T minimum is 10. If it would be 20, then this value will be 10. If it would be 30, this value would have been 15. So that's how. So 85 plus 5, it will be 90. 85 minus 5, it will be 80. So 90 degrees centigrade hot pitch temperature. 90 degrees centigrade is hot pitch temperature. 80 degrees centigrade is cold pitch temperature. hot utility is 20 kilowatt, cold utility is 60 kilowatt, and you have calculated these values from the graphical method as well. So as you can see, both these methods have provided you the same answer. But obviously, I hope you can say with confidence that problem table approach is much easier than the graphical method. Now, coming to the next point, we will draw the grand composite curve, and that curve represents the heat recovery region. Now, this is the curve drawn. This curve gives us the information about the pinch point, which is a pinch point, and it helps us in identifying the above pinch and below pinch region. Like this is the pinch point dividing the system over here. This is the above pinch system. This is the below pinch system, and this information is useful when we will be going to the heat exchanger design system. And as you can see, above pinch there is only heating duty requirement. Below pinch there is only cooling duty requirement. But you might be wondering how this has been drawn. So this has been drawn from your previous slide. If I take you back from this one, if you take this region, this is the feasible cascade region, it will help you. 165 degree centigrade 20, 145 80, 140 82.5, at 85 0, 55 75, and 25 a heat load of 60. As you can see, the same has been drawn over here. And now we will draw it and we will get the same diagram as you are getting it now. How? First we need to draw graph paper, net heat flow, shifted temperature. Now at this point it is 20, at this point it is 80, then 82.5, then 0, then this point which is 75, and then 60. So these are the same points which we have got manually and we have now drawn in the point. So this grand composite curve, now how this composite curve gives us the information about the heat recovery region. As you can see, I have divided these two by this green line. So this region, this one, this is the heat recovery region where process to process heat recovery has been used, and this is the same region over here. As I have told you that it is a pinch point, this is above pinch system, and this is below pinch system. This 60 corresponds to cooling duty requirement. This endpoint, the 20, corresponds to the heating duty requirement. And this one, these pockets, these represents the heat recovery region in the system. It means that for this particular system, and similarly for this particular system, which I have labeled over here, that this point and for this point we have required the utility, but for this pockets we have maximized the process to process heat recovery. Now, what is your task over here? Your task is to compute the shifted temperature intervals and draw the diagram as presented for the overall system. In graphical approach, you have used the actual temperatures and you have drawn the diagram, but now you have to use the shifted temperatures and you have to draw the same diagram, and you will see that you are getting the pinch point over there, and compute the value of pinch temperature from the curve and compare it with actual value obtained from problem table approach, and obviously you will get the same point over here. Now coming next, data extraction, that from flow sheet how we can extract the data. This I will take you to directly to this point. Now we have been given there are two columns, distillation columns. This is the condenser duty, this is reboiler duty, and stream temperature and heat duties are already given over here. Now we can start from here, this point, that how we can extract. If we have been given this flow sheet, how we can extract the data. We can say the stream is entering at 20 degrees centigrade, it is leaving at 0 degrees centigrade, and the total heat load of this stream is 0.8 megawatt. I hope it is clear to you. Then going here, it is at minus 19 degrees centigrade, leaving at minus 20 degrees centigrade, and the heat load is 1.2 megawatt. Then it is entering at 19 degrees centigrade and leaving at 20 degrees centigrade, and it is 1.2 megawatt heat load. First column is completed, 1, 2, 3, 3 streams, and their heat loads were given. In this case, there might be a case that you might be given the CP values. That is absolutely fine as well. Then this stream is going over here. Now it has entered in the distillation column. Here the composition will change and we will not count this stream over here. So this stream is leaving from here minus 39 degrees centigrade, heating to minus 40 degrees centigrade. This minus 39 to minus 40 means it has been heated, and then minus 40 to 20, it means it has been cooled, and its heat duty is 0.6 megawatt. Then minus 1 to 0 degree centigrade, 0.8 megawatt. 0 to 20 degree centigrade, 0.2 megawatt. So you can see the same way this extracted data has been plotted. Plus 20 to 0 with a heat load of minus, obviously 0 minus 20 multiplied by Cp, it will be heat load calculation. Then minus 19 to minus 20. Simply minus 20 minus minus plus 19. So it will be minus 1. Since the answer is in minus, so obviously it is a hot stream. Then minus 40 to minus 40 plus 39. So it will be minus 1. So it's also a hot stream. 20 minus 19. Answer is positive. Cold stream. 0 minus minus plus 1. So plus 1 is the answer. Cold stream. It is a cold stream and it is a cold stream. So there are 4 cold streams and 3 hot streams in the system, and we have extracted this data from this diagram. So there may be a possibility that in exam paper or in some quiz you might be given this diagram with some variations, and you may be asked to extract the data and do the heat exchanger networking or calculate the heat utility requirements for it. So I would suggest you to perform problem table analysis for this and see the values which you have achieved over here. And your homework task is to extract the data from this diagram. You can see there are 4 exchangers: 1, 2, 3, and 4. 20 to 180, 250 to 40, 200 to 80, and 140 to 230. And the heat loads are given, and you have been given this value of delta T minimum, and you have to apply the problem table approach and graphical method to provide me the answers, and this is linked with your one attendance. So that's it from this lecture. Thank you so much.